Okay, exercise 3. This one, it's not hard, but we got to put a couple of things together in order to understand how to do the question. Okay, so let's read the question. At the post office, Cliff, a postal worker, places a 0.6 kilogram package on a scale, compressing the scale by 0.03 meters. A, and we're only going to worry about A for right now. What is the force constant of the spring in the postal scale? Okay, so forget about B for right now. Let's focus on A. First, what we need to do is we need to highlight what we know. So we know that the scale, the package mass is 0.6 kilograms. And we also get a displacement of 0.03 meters, right? That's what we know. So now it gets a little, I don't want to say tricky, but it's like, it's not as plug and play, at least super easy version of plug and play as the other ones. So it's saying, let's circle what it's asking us, what the force constant is. So a couple things to remind you guys, that the force constant is K, and the force constant is a measurement of the stiffness of the spring. Okay? So let's start with that. I'm trying to cover up the next question. Let's start with our formula that we know for sure. We know that the restoring force equals the force constant times the displacement. So the force that you want to bring this scale back up is the restoring force, which is the force constant times the displacement. Okay? So let's get an image of our spring right here. So this is our scale, right? Our restoring force, remember, force constant times displacement is the force. Let's get the video. Let's get our picture. It's the force that wants to move it back up. So the force that pulls it back and attempts to restore the spring to equilibrium is called the restoring force, right? This is the formula. It's this right here. The force that's bringing it down has to do with the weight of the package. Mass times gravity equals the force bringing it down. Okay? So, another thing we need to know, it's okay if you're getting a little bit confused, but just go with it for now, you'll get it. The force that acts to move the spring away from the equilibrium position, which is the force that brings it down. Like when you step on the scale, that's what this sentence is talking about. When you step on a scale or this package gets put on a scale, that's the force that acts to move the spring away from the equilibrium position. In this case, the scale is going down, so that's away. Now this is what's important. It's equal in magnitude to the restoring force. We know it's in opposite directions, right? So all that means is, hopefully you guys can still see that, is the force that pushes the scale down from putting this package on it equals the restoring force, which is the force that brings it back up, okay? So, what does that tell us? The force pushing it down is mass times gravity. So let's go back. I know we're going in a little bit different order, but that's okay. So now that we got this, and rewatch the video if that confused you, and you'll get it. The force pushing down is mass times gravity, and they're saying that equals the restoring force, right? So what that means is restoring force, which is K times X, equals the force pushing it down. So now we've got a good formula to work with. So now, with that being said, let's write down what we know. Okay, we know that number one, our mass is 0.6 kilograms. I'm going to put 0.6. It's the same thing, just so it's easier to see that 0.6. We also know that our displacement is what? Displacement means that movement from the original position, 0.03 meters. So 0.03 meters. So that's our displacement. So we know this. I'm going to put a little dot in what we know. We know our displacement. We know our mass. We know that we're trying to find the force constant. And if you remember from our formula, restoring force equals force constant, that's K, right? We don't know this, times displacement, which is this whole thing. Restoring force, the force bringing it back, right here. So we don't know this. Star, I don't know. That's my star, right? G, remember that's gravity. Mass times gravity equals the force down. So if we remember from our earlier chapters, gravity of the Earth, we do know this. We don't see it in here, but we know it. We know the gravity equals, hopefully you remember this, you've probably heard it a billion times at this point in your units, 9.8 meters per second squared. Meters per second squared. So now we have three things. So see how it's all coming together? We have our mass, 0.6 kilograms. We have our displacement, 0.03 meters. And we have our gravity, 9.8 meters per second. Okay, lots easier. We want to find our force constant. Reminder, force constant, K, is the measurement of the stiffness of the spring. Just how stiff the spring is. That's what they want to know in this. So we wrote our formula. Next we're going to do is we're going to plug everything in. K, we don't know K. That's what we want to find out. Times, X is the displacement. What is that? 0.03 meters. 0.03 meters. In parentheses, that means multiply. Should equal mass, 0.6 kilograms, so 0.6, times gravity. What did we say gravity was? 9.8 meters per second. So 9.8 meters per second. Okay, cool. So now that we know all this, let's keep going. Bam. So I'm going to put a line here, and I'm going to start right here, right? Just so you know. This is where I'm starting. I'm going from 1, 2, 3. So this is my step 3, step 1, step 2. Cool. So let's combine what we can and rewrite the formula. So we still have K times 0.03. Don't forget this point because it'll screw it up if you don't put it. Equals, so now we got to do 0.6 times 9.8 meters per second. So we're doing 0.6 times 9.8. That should give us 5.88. Right? So that we should be sitting at 5.88. So we have K times 0.03 equals 5.88. So now we're going to do it again. I know we're breaking this up in a lot of steps, so that way if we have to look back at this problem when we get to another problem, we're like, crap, I forgot what I did. We need to be able to see all the steps. If I just wrote this and then I wrote the final answer, well, that doesn't help us when we get to exercise like 5, 6, whatever. So that's why we got to break this up. So now we're at 4. Now what we have to do is we have to get the K by itself. So I'm going to do that in step 3 just to show you what we're doing. Is we have to, since it's multiplying here, we have to divide it out. So we're going to divide 0.03, neutralizes that, divide 0.03. So now we have K equals 5.88 divided by 0.03. Okay, so let's do that in the calculator. 5.88 divided by 0.03. And that should give us, we're going to make it another step. K equals 196 newtons per meter. So that's our units. So we can come down here for answer A. We get K equals 196 newtons per meter. We got it. Awesome. So now we've done answer A. It wasn't that bad. We had to write a little bit, but that's okay. We got the right answer. Now let's go to answer B, because I didn't want to cluster our minds up with A and B. I wanted to just focus on A. So now we can look at, let's flatten this out. Now we can look at B. What happens to the force constant if Cliff weighs a heavier package? Okay, so remember, let's block out all this stuff. Block it out. We don't really need this. The force constant here Because if we remember, the force constant is K, right? All that affects the force constant is displacement and the restoring force. Restoring force equals force constant times displacement. So in that question, what happens if he weighs a heavier package? That's mass, right? So what happens if he changes the mass and makes it a lot more? Well, that's not in that formula. So that has nothing to do with the force constant. Which, remember, the force constant is just the measurement of the stiffness of the spring. Well, does that have anything to do with the mass of the package, how stiff the spring is? No, it doesn't. It's just the stiffness of the spring, period, right? So for answer B, what happens to the force constant if Cliff weighs a heavier package? Well, nothing. Nothing happens. It's not going to change. So you could be like, no change at all, or whatever you want to put. Because the force constant is independent. In other words, it is not affected by the mass. Right? The only thing in this formula that's affected by the mass is the force down on the scale, because that's mass times gravity. But the force constant just has to do with the restoring force and the displacement, right? So there we go. We did the whole thing. We did exercise 3. We just stick with what we know, and it's an easy problem. Awesome job. If you get confused, rewatch the video. You guys are going to do great. Don't worry if physics confuses you, okay? Don't worry if it's like, man, this is just blowing my mind, because I've been here. It blows your mind, and you're like, crap, I'm just not getting this. Worry about, do I know where to plug things in? Work on knowing where to plug things in, and when you guys get good at that, okay, I need to use this formula, I know I have this, and I need to find this. The understanding will come, okay? So relax, stick with what you know, plug in the right formula based on what you're given. Make drawings. Sometimes drawings help. You can visualize it. And then you'll understand, okay? Awesome job, guys. Goodbye.